Hello everyone, hope you're doing good. Welcome back to my channel. Today I will be posting the solution for the day 23 of the October Daily Leetcode Challenge. And the question is regarding trees. And we have been seeing questions regarding trees from the last few weeks onwards. And this is one such question. See, when it comes to trees, there are so many aspects of it, okay? The traversals, the DFS, the BFS, the pre-order, post-order, in-order traversals, and all those things. So they are the basic levels. But when you see this kind of questions here, it really tests your logic of how well you understand the trees, because just by simple travel search you will not be able to solve this kind of questions. You will have to analyze in depth where you can modify the what you know so that you can get the answer for this. This is one such question. So today's question is 2641 cousins in binary trees 2. Okay, so yeah, given the root of a binary tree, replace the value of each node in the tree with the sum of all of its cousins value. Okay, so we'll see that in the example, but let us see in the question. Two nodes of a binary tree are cousins if they have the same depth with different parents. Okay, return the root of the modified trees. Note the depth of a node is the number of edges in the path. Okay, all these things are there, fine. So let us come to the question first. So what is happening? First of all, see the last layer, that is 1, 10, and 7. Okay, see this layer, and in the left side you are seeing the question, in the right side you are seeing the answer. So what we have to do is, see, one thing is very clear, we have to return the root. Okay, we have to return the root of the solution tree. Okay, one thing is very clear. So what, how the answer is coming, let us see here. So if you see here, for the node 1 and 10, the parent is 4. Okay. 7, which is also in the same depth. What is depth basically? Depth means the distance from the root. Okay. In this case, if you see, I have two edges, that is 5 to 9 and then 9 to 7. I have two edges. Okay. Similarly, when I see the depth of 10 and 1, again I need to traverse two edges from the root. That is from 5 to 4 and then from 4 to 10, or from 4 to 1. The same two edges I will have to travel to reach this. That is 1, 10, and 7 are at the same depth. Okay. That is the basic idea. Now, see the thing here. 7 is not, you know, a cousin of 1 and 10. That is, it doesn't share the same parent. Okay. For example, 1 and 10 share the same parent, but 7, though it is in the same depth, it does not have the same parent. So in this case, it will be a cousin, but not from the same parent. So in this case, what you have to do, for 4, that is from 1 and 10, you will have to replace it with the sum of the cousins which are at the same depth. Okay. So see, if you see the question here, yeah, replace the value of each node in the tree with the sum of all of its cousins value. Okay, so the two nodes of a binary tree are cousin if they have the same depth but different parents. So this particular scenario, qualifies for that. Okay, what is happening here? You will have to replace 1 and 10 with 7. Okay, one thing is very clear. Now, for what we'll have to replace with 7? See, 7, 1 and 10 are cousins of 7. So we'll have to replace 7 with 1 plus 10, which is 11. That is the basic idea. Okay, I hope you are understanding what I'm saying. Okay, two nodes of a tree are cousin if they have the same depth but different parents. Remember, 1 and 10 are not cousins of each other because they share the same parent. Okay, 1 and 10 are not cousins, but 7 and 10 are cousins. 7 and 1 are cousins. So what I'll have to do, you have to calculate the sum of the cousin nodes which are at the same depth, and you have to replace that particular sum with the current node's value. Okay, let us see the case of 4. What is there any cousin of 4? See, there is no cousin of 4. See, what is a cousin, by the way? Cousin means something which is at the same depth but does not share the same parent. In this case, though 9 is at the same depth, but still it is not a cousin. Okay, because their parents are not different. So 4 doesn't have a cousin, so the sum of the cousins will be 0. Sum of the value of the cousins will be 0. Same as the case for 9, it will be 0. Okay, one exception here is that if you see, though in the question they have not mentioned, but 5 also does not have any parent or any cousin. When it doesn't have, okay, you're getting it right. Always the root will be always this, single element, that particular depth. Okay, always there will be one root only of a tree. Okay, so it will be by default always 0. So this you have to take it as an edge case in this particular question, and always you have to replace the root with 0. Okay, so that is the basic idea. Okay, you can see the other question as well in this particular thing also. If you see, none of the nodes have a cousin, so all of them will be replaced with 0. Okay, I hope you're understanding what it is. See, cousin here basically means, okay, the node should be at the same depth as the current node, and they should not have the same parent. Okay, two nodes have a binary tree are cousin if they have the same depth but different parents. The parent should not be same. What you have to do, replace the value of each node in the tree with the sum of all of its cousins value. I hope you are getting the question now. So what you have to do, see, my approach which I am going to show, it's very, very simple. So what I will do is, first of all, I will calculate the sum, okay, at each depth. That is sum of all the nodes at a particular depth I will calculate. Okay, yeah, so what I'm doing it here, see, if root is none, simply return as it is. Okay, I'm using a map here. Okay, this map I'm going to use to store, the what is the key will be the depth, and the value will be the sum of the nodes at that particular depth. Okay, so this I'm doing a DFS algorithm. Okay, a simple DFS algorithm, and I'm calling this DFS algorithm here. Okay, so what I'm doing here, simply DFS. So what you have to do is a simple DFS. Okay, I'm not doing anything extra here. If the root is none, simply return is this is part of the DFS algorithm. I'm not doing anything extra. But if you see here in the parameters, I'm taking one thing extra, that is L equal to 0. The default value is 0. What it means, this is basically the depth. Okay, so what I'm doing is, see, this is again a simple DFS. This is again a simple DFS. There's nothing extra here. What is the extra thing coming? This is the part which I'm adding extra. So what I'm doing it here, if L is not in A, okay, that is if I am visiting a node in that particular depth for the first time, what I have to do, A of L is equal to root of L. Okay, that is the value. For example, let us say I am coming to depth 2 for the first time. That is, I am coming to the node 1 for the first time. Okay, that means I have not visited any node at this particular depth previously, so this is the first element in this particular depth. So I will take the value as the value of this, that is a of L will be 1 in this case. Okay, if this is not the case, okay, if this is not the case, what that means, I have already visited somewhere in this particular depth. Okay, in that case this will be used. What I have to do, whatever value is already there, simply add the current node's value to it. Okay, as simple as that. So ultimately what we will have, a of L will be, it will be sum of the root dot val of all the roots which are present in that particular depth. Okay, I'm calculating this sum of all the values present at that particular depth. Okay, as simple as that. So once this DFS call is done, this particular function will be executed, and by the end of this function we will have the sum of all the values at that particular depth for all such depths. Okay, that is the basic idea. Now I'm using second DFS function. In this, what I'm going to do, it's again exactly same as what we have done previously, but there is a catch here. What I'm going to do, see, this is a function call for the second DFS function. Okay, what I'm doing it here, see, again the same thing. If root is done, simply return it. Again, these two things are same. I'm taking root and I'm taking the depth. Okay, L is the depth basically. Okay, so this is the same thing as it is. Okay, while here also, while I'm doing the difference of root dot depth left comma L plus 1. Why L plus 1? Whatever is the current depth, you have to add 1 to it because you are going to one depth below. Okay, same is the case for DFS of right. Okay, root dot add comma L plus 1. Here also I'm doing the same thing. Okay, just as the previous one, but remember here I'm calling DFS function, here I will calling the DFS2 of function. Okay, DFS2. Okay, so what I have to do, remember, whenever I'm at the parent, I know what are going to be the child nodes. Okay, I can access them, so I will use that logic here. I see, once the diff is done, that is once I do, I go to the child nodes, I do whatever processing needed and come back. So what I will do then, I will declare a child some value, initialize it with 0. Okay, if the root dot left, okay, is it, if it is not none, okay, that is in the left of the current node there exists a child node. What I will do, child sum is equal to root dot left dot val. Okay, that is I'm adding, see, child sum is 0, child sum is equal to child sum plus root dot left dot val. That is when the root dot left is not none, that is when the left, I can say a node that is in the left of the current parent there exists a child node. Okay, take its value and add it to the child sum. Okay, same is the case for the right. If in the right, if the right pointer of the current node, that is if the parent has a right node, okay, in that case simply take the value of it and add it to the child sum. Okay, child sum as it is. Okay, these two parts, I'm simply calculating the child sum, these two things. Okay, after that I will be using the child sum in these two cases. I will be using the child sum. What I'm going to do, if root dot left is not equal to 1, that is even if in the left there is a a child node existing, what you have to do, replace its value. Okay, that is root dot left dot val is equal to a of L plus 1 minus child sum. That is the sum of all the elements. That is, see, what is, whenever I'm referring a, what is a, basically, as I mentioned it here, a is actually a map. Okay, what it will store at a particular depth. Okay, what is the sum of all the nodes value, okay, at this particular depth. So what I will be storing, I'm taking in the, see, L plus 1 means in the depth in which the child is there. Okay, take the sum of all the elements, okay, divided by the child sum. So if in this case I can show you what it means. See, let us say I'm at 4 and I'm doing this particular calculation. So what is the child sum? First of all, it is 1 plus 1, which is 11. Okay, you have to take 11. And what is a of 2? In this case, a of 2 will be 1 plus 1 plus 7. Okay, that is, it will be 18. Okay, a of 2 will be 18 because the sum of all the nodes. Okay, in this case, it will be, a of 2 will be 18. From 18 we have to subtract 11. Okay, what is 11? 1 plus 1 is 11. So 11 minus 7, that is 11, sorry, 11 minus, sorry, it will be 18 minus 11. Okay, so you will get 7 here, as simple as that. So basically take the sum of all the nodes which are at that particular depth, subtract it from the child sum, that is sum of the values of the child node. Okay, as simple as that. Same I'm going to do with the right also. Okay, if the right node is not none, not none, then what have to do? Replace its value with a of l plus 1 minus child sum. Okay. As I mentioned, this is edge case. Because see what I'm doing it here, from the parent I'm going to replace the value of the child, because the root will not be having any parent, so its value you have to change by default. Okay. And then you have to return the root as it is. So let me quickly run this and show you how it works. Okay, like maybe for your benefit I can print and show a also, because this will be confusing for you, because I have not given the appropriate names in this particular case. So let me quickly show you this also. Okay, this is what A looks. Okay, A of 0 is 5 initially. Remember, this is before doing the processing. Okay, after the device function is called. Okay, so initially A of 0 is, that is at the depth 0, there is a node of value 5. That is the root node. Okay, A of 1 is 13. Okay, that is 9, 4 plus 9 is equal to 13. Okay, similarly, at the depth of 2, I have the sum of 18. What it means 1 plus 10 plus 7, which is 18 in this case. Okay, this is what it is. Okay, so in this particular calculation, we are using that. Okay, take the sum of all the nodes that are present at particular depth, subtract with my child sum. Okay, this is done at the parent level. Remember, this is being done at the parent level. Okay, I am referring to the child nodes. Okay, I am referring to the child nodes value. Remember, I'm not accessing them directly from the parent. I'm accessing the child nodes value. That is when I'm at 4. When I'm at 4, I will be replacing the value of the child nodes. That is 1 and 10. Similarly, when I'm at 9, I will be replacing the value of the child node, which is 7 in this particular case, to replace with 11. Okay, from the parent, I'm accessing the child nodes value. I'm doing it. Okay, that's what I'm doing. So let me quickly run this and show you. I've already shown you how the values of A are being populated for the example 1, and how the final answer is populated. Yeah, you can see both the discuss are getting accepted. I've already submitted the solution, so you can do the same. I will give you the link of this particular question in the comment section below, in the description section below. You can go through it and check it out. This is a nice question basically. See, do not expect simple traversal algorithms. If you are targeting for something good, during your interviews, you should be knowing how to manipulate the algorithms, depending upon what you need. Okay, simple traversals, simple in order traversal, post order, pre order traversals, or simple device will not be helping you in such approaches. Okay, in this particular question you have to, you are very clear basically what is the requirement. So you are, the traversal as it is will not be helping you, so you have to modify them based on your need, and you have to do it. Okay, in this case what I'm doing, I'm using a DFS. I, modifying it to include the depth parameter, and I'm calculating the sum of all the elements at a particular depth. Okay, that I'm going to use it from the parent. I'm, accessing the child node's value, and then I'm replacing it with a particular value, which is, sum of all the nodes at that particular depth minus the child sum. Okay, that is the value of the child's that a particular parent has. I'm subtracting it with that. Okay, then I'm getting the value that I'm replacing it here. Okay, one optimization that you could have done is that instead of, calculating these things two times. Okay, here if you see, this and this are same and it's being calculated two times. So maybe before doing this, you could have saved that value in a parameter, in a, variable, and then you could have assigned that variable directly here. Okay, instead of doing this calculation two times. That is something that we could have done. Okay, yeah, that is fine. So one thing is very clear. See, if a particular node belongs, so the idea here is, see, each parent's node. That is, if two nodes belong to the same parent, they will have the same value in the answer. That is one thing that I would like to highlight and say it to you. Okay, that is just one observation based on this particular question. So yeah, that was all for today. If you like my efforts, please do consider subscribing to my channel. If you have any other better way of doing this, then also you can please post it below so that we can discuss it further. Thanks a lot. See you tomorrow.